Hello everyone, last time we started Enolate chemistry and we have covered the aldol condensation. So today we are going to start the Claisen condensation. Claisen condensation is basically three type. The one self, second crossed, and third intramolecular. So in this video we are going to cover all these three. Intramolecular Claisen condensation is also called as Dieckmann condensation. And self and crossed, self means two same mole of ester molecule and crossed means two different mole of ester molecule. So let's start the very first one, self Claisen condensation. Self Claisen condensation. So here the condition is the very first two same mole of ester must have alpha H. Means those ester molecule which must have alpha H, like this one suppose. So here we have 2 mole of ester. You can see the left one, this is carbonyl. So carbonyl neighboring carbon is alpha, but there is no alpha. This carbonyl neighboring carbon is alpha, and here we have alpha carbon as well as alpha H. So it can give you self-Claisen condensation. But this mole cannot. The reason is that they don't have alpha H. Clear? So if we are going to discuss the mechanism of self-Claisen, so we have this mole of ester supposed to be CH3 C double bond O OCH3. So here the base will be my OR1. This is oxygen containing carbon will be the base. So we can say CH3O minus Na plus. This mole is using as a base. So what is mechanism? And 2 mole. If 2 is not given, only this thing is given, then it means it has 2 mole. Okay. So 1 mole is used to generate a nucleophile, because this base grabs this alpha H, which is very acidic. So it will grab this hydrogen. So here we have CH2 minus C double bond OCH3. Now we are going to introduce another mole of ester, because we have 2 mole and both mole are same. And this is the condition of self-Claisen when the both ester molecule are same. If they are different, then that is called as crossed Claisen. So this negative attack over this carbon and this bond is going to break. So OCH3 is my leaving group. This kind of attack is called as nucleophilic addition then elimination. So this is also called as nucleophilic acyl substitution. So this OCH3 leaves, and now we can add like this CH3 C double bond O, this part, and then CH2, and then C double bond OCH3. So this carbon is alpha, alpha neighboring is beta, so product is beta keto ester. Beta keto ester. Clear? So this is called self-Claisen. How we can write down the trick of this reaction? So look at here, we have suppose this ester. I say 2 mole, it means we can write down the both moles like this. But 1 mole we can show the alpha H. Clear? Like this. So here you have to remove the alcohol. Alcohol means this OCH3 and 1 alpha H. Overall it is methyl alcohol. So OR means this oxygen CH3 is a leaving group, and here alpha carbon only 1 alpha H. This is my alpha. So we can remove this methyl alcohol and we have to connect this. So the product will be CH3 C double bond CH2 and then C double bond O CH3. So this is my alpha, this is my beta. So the product is beta ketoester. Clear? So this is the trick of Claisen, self-Claisen condensation. We can discuss another one. Suppose we have this one. So first mole we can same write down like this. Second mole we can show or alpha H, okay, alpha H like this. This is the alpha carbon and it has a 1 alpha H. Now we have to remove the alcohol, so this goes out. Now we are going to connect these both component. Now look at this, carbon is directly bonded to this carbon. This outer carbon has a C double bond O and then OCH3. So this is alpha, this is beta, so this is beta ketoester. Makes sense? This is self-Claisen. Sometimes we have a retrosynthesis as well. Retrosynthesis means from product to reactant. Suppose we have this beta ketoester. This is our product. Shit, give me 1 second. Yeah, this is the product and we have to find out the reactant molecule. So simply we have to break the alpha beta bond. This is ester, so ester neighboring alpha, alpha neighboring beta. So break this bond, alpha beta bond. We all knew Claisen condensation, we have to remove the alcohol molecule from reactant to product. So it means once you have a product and you have to figure out the reactant, then you have to add alcohol. Make sense? So reactant to product is a removal of alcohol. So product to reactant is the addition of alcohol. So we can write down like this. A carbon have a 3 hydrogen and here O and here H like this. So what will happen? We have to remove, means even you can write like this, wait, CH3OH we can write down in this way, CH3OH, O have a H and this is OCH3, clear? So this alpha will grab this hydrogen, so it becomes CH3, COCH3 like this, CH3, COCH3, and this mole also once it is going to attack this CO with OCH3 like this. So this is also my reactant CH3 C double bond OCH3, clear? So this is retrosynthesis, means from product to reactant. Now the next is crossed Claisen. In crossed Claisen, two different mole of ester, but any one must have alpha H. Makes sense? Like crossed aldol means any one must have alpha hydrogen, like this. Makes sense? Again, the simple thing is that we have to remove alcohol molecule, means from alpha containing carbon, we can remove alpha hydrogen, and the ester which don't have alpha carbon, then we can remove its OR part. So like this, we can write down this one in this way. So this mole has no alpha hydrogen, so we can remove its oxygen part, means OCH3 group. This side have alpha H, so we can remove its alpha hydrogen, so we can expand the alpha hydrogen like this. And now remove the alcohol. Alcohol means this OCH3 with this H. So what should be the product? H, C double bond O, and then CH2, and then C double bond OCH3. So this is alpha, this is beta. Again, we have a beta keto ester. Okay. So this is crossed one, and the trick is very simple. And if you are going to write down the mechanism, so base will grab first alpha H, so it will form this nucleophile. Clear? And this nucleophile attacks to the another mole of ester like this. It will attack over here and it leaves. So simply you have to just attach this. So HC double bond O and then CH2COOCH3 like this. So this is alpha, this is beta. Makes sense? Now next is intramolecular. Intramolecular is also called as Dieckmann condensation. So, both ester in a same reactant molecule like this. And this is the base CH3O minus Na plus. Look at here the trick. If you want to write down the product directly, so you can start numbering from alpha carbon to another carbonyl molecule. Again, listen me. Alpha carbon to another mole of carbonyl. So this is my alpha. Start numbering like this: 1, 2, 3, 4, 5. Again, start numbering from alpha carbon to another mole of carbonyl. So this is the carbonyl. So you can see you have 5 member ring. How many member of ring? 5. From 1 to this carbonyl is a 5 member ring. So we can draw like this 5 member ring, and we can do numbering as well: 1, 2, 3, 4, 5. And start numbering in the ring from anywhere, it doesn't matter. So now look at the connectivity. So one has this group ester, so one has outer side ester, and number 5 have this carbonyl bond. Always draw the carbonyl only, not this one. Do not draw this one in the ring. So CO is here at number 5, so C double bond O at number 5. So this is my alpha carbon, alpha neighboring is beta, so this is beta keto ester. Simple. So how can it be possible? If you are going to write down the mechanism, the first step is what? Base grabs this alpha hydrogen, so there is a negative charge. So here you have 1 mole of ester, this is a nucleophile, so it attacks over this carbonyl, and this group going to leave. That's why it is not in the ring structure. Make sense? We have another question, so look at here. We have few more groups. So how we can draw the product? Listen me again. You can see, start numbering from alpha carbon to another mole of carbonyl. So this is my alpha carbon. This is 1, this is 2, this is 3, 4, 5, and this is 6. And do not draw this one because this is a leaving group, okay? So we have 6-member ring. So 6-member ring like this. And start numbering from anywhere in the ring. Suppose this is my 1, this is 2, this is 3, 4, 5, and this is 6. So you can see one has esters, outer side ester. So just draw like this, C double bond O, C double bond O, and then O with 2 carbon. And number 6 has a carbonyl bond, number 6 has a carbonyl. Simple. So this is alpha, this is beta. Beta keto ester. Okay. So simple. Any doubt? And once you have a product and you have to figure out reactant, look at this one. Suppose what should be the reactant? So look at here. Very simple. First mark the alpha beta ester neighboring alpha, alpha neighboring beta. We know that this ring is a 5-member ring, and once you have to break the double bond, this alpha beta bond, so you can see the numbering here 1, 2, 3, 4, and 5. Now draw the 5-member straight chain. 1, 2, 3, 4, 5. So one has outside ester, double bond O like this, and this is 5 has a carbonyl, and you have to copy this part you have to copy. So oxygen with 2 like this. So this is the reactant, from product to reactant. So this is all about the intramolecular, which is also called Dieckmann condensation. So we have covered 2 name reactions. So one is aldol, second is Claisen. What is the basic difference between aldol and Claisen? So look at here. Reactant, first of all, you should know what is the basic difference in terms of reactant. Here reactant is our aldehyde or ketone. And here we have ester. And what should be the product? Here alpha beta unsaturated carbonyl. And here you have beta keto ester. So most of the students is struggling in the aldol and Claisen. So this is the basic difference. Aldol always have aldehyde and ketone as a reactant, and Claisen always have ester as a reactant. Aldol final product alpha beta double bond containing carbonyl, while Claisen have beta keto ester. Make sense? So this is all about the aldol and Claisen. In the next session we will start the Robinson annihilation and Michael addition. This is also very important. Okay, so thank you so much for watching this.